Good afternoon, everybody. Let's get started with the class. For announcements, homework 8 is posted. That's not due until next week, so stop by office hours if you have any questions about that. Lab is complete, so you're all done with all your lab assignments. Congratulations on getting your project done. I think everybody did a really great job with that propeller test bed. Be sure that you have returned or will return the component case. You can keep all the components for the lab that you got during the lab and you used, but you need to return that orange and black case to the ITLL and also empty out your locker and leave the locks unlocked. So be sure to do that. All right. So during the previous class, we talked about transmitter and receiver architectures, and we started on antennas and antenna patterns. And so this time we're going to continue with antennas. And we talked about last time how antenna patterns represent how an antenna radiates power and in what direction. So this was a two-dimensional antenna pattern showing that the maximum radiation of this antenna is toward the 90-degree direction in this case. And then I showed you a three-dimensional pattern, which really is the real case for an antenna. An antenna radiates in 3 dimensions. So you can look at these three-dimensional diagrams and see the true radiation pattern, the power versus angle in spherical coordinates. We usually use these two-dimensional patterns. They're a little easier to interpret in sometimes what we call the principal planes. So you'll often see two-dimensional antenna patterns. Antenna patterns describe whether an antenna is directional, in other words, it radiates most of its energy in primarily one direction, or if it's isotropic or mostly isotropic, if it radiates its energy kind of in all directions equally. There are different cases where you want each of these. In other words, if you have, let's say, you don't know where your intended receiver is, you might want an isotropic or an omnidirectional all around you radiation pattern because you don't know where to direct the energy. If you do know where to direct the energy, you might want to have a directional pattern. Let's say you have a point-to-point communications link, maybe a microwave link. You want to direct your transmit power toward the receiver so that that you can use the minimum amount of transmit power and also cause minimum interference to other receivers who may not be intending to receive you. Okay, so there is value in understanding antenna patterns. They describe the gain versus direction of antennas. Here are some real practical antenna types. So there are many antenna types, and you typically select an antenna for your application based on the peak gain you need, maybe in a certain direction, the shape of the pattern, if you need it to be directional, omnidirectional, or close to isotropic, the bandwidth of the antenna, the polarization of the field radiated by the antenna, and when you're looking at the physical package, the size and weight of the antenna, and the complexity and the cost of the antenna. A very common antenna is the dipole antenna. A dipole antenna is an antenna that has a feed point in the center and has two legs coming out from that center. And those legs are typically a quarter wavelength long, so that sets the size of the antenna. The pattern of the dipole antenna, the radiation pattern, looks something like this. In this case, the dipole would be oriented along the z-axis. It's kind of in the center of this apple-looking thing. There's a null at the top and a null at the bottom. So the dipole antenna has nulls off of the end of its legs. If you look along the direction of that leg and project it outward, there's very low radiation out practically in that direction. Okay, this is a more expensive dipole antenna. You'll see simple dipole antennas that are just a feed point with wires, just approximately quarter wavelength wires running out in each direction. But they're very effective if you need a pattern that looks like this. If you need a highly directional pattern, you might use something like a parabolic reflector antenna. These are usually used to communicate with satellites, which are up in orbit very far away. And they have more of this pencil beam They direct their energy primarily in one direction with a very narrow beam width. Okay, but they have very high gain, so that maximizes the power that you're using on transmit to get most of that power toward the intended receiver. In this case, if it's a satellite, the location in orbit. If you need a little less gain, but you still need a directional antenna, you can use a Yagi antenna, sometimes called a Yagi-Uda antenna or Yagi-Uda antenna. Uh, these antennas have relatively high gain in that sort of 8 to 10 dB up to 15 to 20 dB. They have varying numbers of elements, but that pattern looks something like this. You'll see these on some point-to-point links, yeah, some VHF communication antennas, UHF communication antennas, Wi-Fi antennas, where you have to get from uh, uh, a point to point. So you don't want to transmit or receive in an omnidirectional pattern, but you want to direct your energy in a particular direction. And then you'll see sometimes for omnidirectional patterns where you have a wideband need for an antenna. This is a discone antenna. So it's fed between this cone bottom and this round disc top, and it gives you an omnidirectional pattern in azimuth. And because of its geometry, it's wide band, so it can cover very wide range of frequencies typically. If you're trying to put an antenna on a circuit board and build it into a product, maybe with a plastic case, you'll see microstrip patch antennas. These are etched on circuit boards. They're relatively low gain. And you'll see these, again, on circuit boards. You'll see these maybe on ceramics in GPS antennas with amplifiers built in. But they're good. In this case, if you have this circuit, here's the patch right here. It's fed with this microstrip transmission line. If this were oriented upward, if you're looking down onto this antenna would look upward toward the sky. Okay, there are many other types of antennas. There's the monopole antenna, like you'll see if you mount an antenna on your car, if you have a kind of a whip antenna coming out of the side of your car or side of your hood facing upward. That's a monopole antenna. You'll see people who use mobile radios, ham radio operators, they'll use magnetic mount monopole antennas. PIFA antennas, planar inverted F antennas, are integrated into some RF modules. A horn antenna can direct energy in a certain direction at higher frequencies. Log periodic, that's like your if you have over-the-air, well, we used to use these over-the-air television. Used to use log periodic antennas. They're fairly wide bands. There's slot antennas, loop antennas, helical antennas, broadband Vivaldi antennas. Lots of different types of antennas. And so how do you choose one? Well, you go back and you look at their characteristics and say, what do I need the peak gain to be? What do I need the pattern to look like? How about the bandwidth? How wide do I have to transmit or receive across the band? What polarization do I need? Size, weight, complexity, and cost. So you look at all these antenna choices and you try to match that up with the available antenna designs. So that's what I want to present on antennas. I'd like you to know about antenna patterns, different antenna types. I think you can search the web to see different available choices for these antenna, relative complexity, relative cost when you would use those. But I wanted to especially introduce you to pattern and gain so we could talk about that when we get to link budgets of communication systems. Next, let's talk about radio wave propagation and path loss. So we've gone from the information source through the transmitter to the transmitting antenna, and now we're going through free space or through the air, through space to get to the receive antenna. And so that's where we need to talk about radio wave propagation and how that energy spreads out from the antenna and how it reaches the receive antenna. Power density and effective area describe the energy that is propagating through space, and at the receive antenna, how much energy is collected at that antenna. Let's take a look at an example to describe power density and antenna effective area. Let's suppose you have a point source. So this is an isotropic source. It's radiating radio frequency energy, RF energy, isotropically, which means theoretically with the same pattern, a spherical pattern, the same amount of energy in all directions. And let's suppose you're feeding that point source with PT watts. So PT watts is being radiated from that point source uniformly in all directions. Let's go out a distance D1 and imagine this is a sphere. It's not just a circle, it's a sphere surrounding that point source. Well, that sphere has an area. That area is 4 pi d squared. It's just the area of, and it should be d1 squared. That's just the area of that sphere at distance d1. So if you have PT watts radiated uniformly and all that energy is going through that sphere and that point source is centered in that sphere, you can calculate a power density going through that sphere or at that distance d1. So S is power density, and it's power divided by area in watts per meter squared. So at distance D1, you have PT watts going through area A1, and so that's how you calculate watts per meter squared. If you go out farther and you have a bigger sphere, you have more area, but you have the same energy going through that sphere. Okay, so then you have S2. So you have a bigger area, but the same amount of energy, you're going to have a lower power density. I should say power, I shouldn't say energy. So you have the same power radiating out in all directions uniformly. So you have a lower power density. And then let's go out sphere area A3. Likewise, you have PT, the same amount of power radiating. A3 is the area of that bigger sphere. Okay, so P is constant, but the sphere area increases. Okay, so S is falling as you get farther away from the point source. And the sphere area increases as d squared, right? Because you calculate 4 pi d squared. So the power density falls as d squared. So S is proportional to 1 over d squared. Now let's get farther away from this point source. So you get really far away, and the sphere becomes kind of flat locally, right? There's still theoretically some curvature, but if you get really far away from the sphere and you look at just a local area, it's like standing on the ground of the curved Earth. The field looks kind of flat. Well, that's the same case here. This sphere area right here would look relatively flat to an observer when you're far away from the source. And so that means that this wavefront looks like what we call a plane wave. So if you look at the wavefront, you line up the phases. Remember that the radiated power, right? That signal, the radiated electric field, it propagates so that it has this wavelength versus distance. And if you line up all the, let's say the peaks here, you get a plane. So that's why they call it a plane wave. Now let's introduce a receive antenna. So this is the receive antenna. It doesn't matter what kind it is. I'm just showing it as a rectangle because that antenna, that receive antenna, can be viewed as an aperture, like a window, that collects electromagnetic power. In fact, there's something called effective aperture or effective area. And the size of that, what I'm calling power collecting area or power capturing area, is called the effective area or the effective aperture, A sub E. And it's given in just square meters. It's like a window that is letting the power in and collecting it. So suppose you have a power density arriving at the antenna of S. And let's suppose that antenna is oriented so that propagating power is perpendicular to the antenna area. So if you drew a line out from that point source out to this antenna, that line would be perpendicular to that plane of the receive antenna aperture. Then that receive antenna, now you have a cable connected to it and power comes out of that. That power, that received power, is going to be the power density times the effective area. Right? So you have power density in watts per meter squared times area meter squared, you get watts. So that's the power out of that receive antenna. That's one way you can view a receive antenna, how much power is going to come out of it. There's a relationship between gain and effective aperture or effective area, and you can actually use that effective area knowing the power density to calculate how much power is coming out of that antenna right at the antenna port. If you have cables, there's loss. There could be following components and loss, but right at the antenna port, given the gain right there, you can calculate effective area. You can relate that to how much received power you will get given power density. Now, since the power falls as d squared, the power out of the antenna is going to fall as d squared, right? Power is proportional to 1 over d squared. So that means if you take this receive antenna, it's receiving a certain amount of power, and then you take that receive antenna and you double its distance away from the point source, away from that, or away from a transmitter. That power is going to fall as 1 over d squared. So if you're twice the distance away, you're going to have 4 times less power, or a quarter of the power. If you're 10 times the distance away, you're going to have 1/100th of the power. So that's the relationship that you would see as an antenna, a receive antenna moves farther away from a transmitter antenna. Let's take a look at radio wave propagation in terms of modes of propagation and some phenomena that happen to propagating waves. So when I say propagation, I'm talking about how RF waves travel from RF transmitters to RF receivers. So let's say we have the Earth here and we have these disproportionately large buildings as a cartoon, and I put some antennas around the Earth here. So radio waves can propagate directly, right? They can propagate directly between two antennas. We call that line of sight. Or they can propagate by phenomena including reflection, diffraction, or refraction. Okay, so reflection is when you have this transmitter here. Let's say this is a transmit antenna. Here's a receive antenna, but that receive antenna is blocked by a building. You can actually receive the reflected energy, the reflected power off of a building. That's one mode of propagation that happens. You can also get diffraction over a building or over anything, over any kind of object, right, where you have some kind of blockage in the line of sight. So in this case, this transmitter antenna, its signal would diffract over that building or other object. Okay, you can have a ground wave or a surface wave and ducting depending upon atmospheric conditions. So radio waves can actually, at certain frequencies, kind of hug the Earth and you get a surface wave. Or if you have changing conditions with altitude, you can get ducting along the ocean or different land types. And then if you're going over the horizon, you can actually have ionospheric propagation. Okay. So ionospheric propagation it happens typically at what we call HF frequencies, ranging from a megahertz or 2 or 3 up to about 30 megahertz. They're effective, depends on the condition of the ionosphere. But if a signal is transmitted, it'll actually try to go out into space. It'll travel straight out. But then because of the ionosphere, different times of the day, this changes, different times of the year, depending on sunspot cycles. But you get this refraction where the ionosphere bends the radio waves and they come back down to Earth. So this is one way you can communicate around the world. And ham radio operators do this all the time. They communicate from the United States to different countries, from Europe to South America. I've communicated from the US, central US to Australia on about 80 watts. So it's really amazing how you can get these signals around the world through ionospheric refraction. These modes of propagation depend on frequency. So the diffraction that you get or this ionospheric refraction depend on what frequency you're transmitting at. So for example, ionospheric refraction often works well below 30 megahertz. Sometimes that's restricted to maybe 28, 27, 26 megahertz. Depends on the ionospheric conditions. Okay. So those are different terms you'll hear when people talk about propagation of radio waves. You'll also hear about satellites. So if you have a satellite then that's typically line of sight propagation. So you have a satellite in orbit, maybe it's geostationary, staying in one place like DirecTV, or maybe you have some kind of low Earth orbit satellite and you have to point your antenna or have an array that automatically points. Then that would be line of sight propagation, and you use that to get over the horizon as well, to get over hills, to get around the Earth, etc. Okay, so there's a way to calculate the what we call path loss, free space path loss for a radio wave traveling through space. And this is a way that you're able to predict, given a transmit antenna, given a distance, given, let's say, free space between transmitter and antenna, how much receive power you're going to see out of your antenna at the receive side. And we often want to calculate this. We often want to calculate the desired signal power at a receiver. What that lets us do is estimate the link performance or the system performance. By that, I mean the quality of the receive information. Can we hear the voice without much noise? Can we get the data without many errors? Let's suppose you have a transmitter and a receiver. And so this is the transmitter with its antenna. Here's the receiver with its antenna. And the antennas are separated by distance d. The free space path loss, we're going to call that L sub p, is a way to account for the reduction in power that we see at the receive antenna versus distance, right? We talked about the power density falling as the receiver gets farther away from the transmitter. Free space path loss accounts for that. So this L sub p, this free space path loss, and I'm going to give it in dB here, 10 log base 10 of 4 pi d over lambda quantity squared. And you can see you have a distance squared here. So loss is a reduction in power. And here's your d squared term, right, as power density falls with distance squared. There's an equation called the Friis transmission equation, and it's used to calculate received power, given we know the transmit power, we know the transmitter antenna gain, we know the receiver antenna gain, and we know the path loss. So if you know that, or you can estimate that, we can use the Friis equation. So let's introduce the gains of the antennas. Here's the transmit antenna gain, G sub t, and here's the receive antenna gain, um, G sub r. So G sub t and G sub r are those gains. And the way they fit into the equation is this. You have power at the receive antenna port. This is typically what you want to calculate. How much power do we get out of the antenna port or at the end of a cable? So that's equal to the transmit power plus the transmit antenna gain plus, or minus actually, the path loss plus the receive antenna gain. So if you're trying to get a lot of transmit power, and note I'm expressing these powers and these gains in dB units, power in dBm, gains and losses in dB. So if you want to know, if you want a high enough, higher is usually better, not always, for power out of an antenna. If you want to know, if you want that signal to be relatively strong enough, then you want a high transmit power. That kind of makes sense. You want high antenna gains. They increase your receive power, and you want low path loss. That makes sense. You want to be closer together if you can for a given transmit power, given gains. Okay, so you can add these values together or subtract them when you have these units in dB. Because remember, dB, when you add dB values, that's like multiplication of ratios and powers together. And so a lot of times you can do the addition in your head. It's a little easier than doing the multiplication in your head, but we often work in dBm or dB watts and dB units. If you look at the Friis equation as products and I guess a fraction here, a divide, then PR is PT GT GR over LP. If you don't use dB units, and path loss is 4 pi d over lambda quantity squared. Okay, so sometimes we combine the transmit power and the transmit antenna gain into this value we call EIRP, the effective isotropic radiated power. Okay, and so EIRP is actually PT plus GT. So you combine those together. So you'll hear sometimes a transmitter system has so much EIRP, where you're applying for a license for a transmitter, and they'll ask, what's the EIRP? And then the received power is EIRP, which is right, PTGT, minus LP plus GR. And so what EIRP, it's the equivalent transmit power if we were using an isotropic antenna at the transmitter. So if you had a transmitter with some gain and you use the system, right, and you transmit power in a certain direction and you care about only that direction, if you were to replace that antenna with gain, that has gain, with another antenna that were isotropic with 0 dB, right, you would have to apply this amount of power to that antenna port in order to get the same performance. Okay, so the Friis equation is useful to calculate free space path loss and to calculate power at a receive antenna or out of a receive antenna. And then you can use that power to estimate system performance of the receiver or quality of the information. You can estimate or calculate quality of the received information at the receiver. So grab your clicker apps. Let's do an example of free space propagation, free space path loss, and calculate received signal power. Let me get this started here. All right. Let's suppose you have a transmitter and you have a receiver that is separated by some distance. And that transmitter transmits 1 watt. And 1 watt is 30 dBm. And then you have a transmit antenna that has 7 dB of gain in the direction of the receiver. And you calculate the path loss to be 112 dB. So this is equivalent to free space path loss if you were using 1.2 gigahertz center frequency over a distance of 5 miles, right? We're in the US, we typically estimate distance in miles. And then you have a receive antenna that has a gain of 2 dB in the direction of the transmit antenna. Okay, so what is the received power P sub R in dBm? Okay, so there are your choices. Give that a shot. All right, let's talk about this. This is a realistic situation with practical values. Let's suppose you have a handheld transmitter that transmits 1 watt. That would be acceptable for handheld, reasonable for a handheld transmitter RF power. And then you have a 7 dB antenna. Maybe this is a little high for antenna gain for a handheld. Maybe this is connected to some kind of external antenna. Maybe it's a collinear folded dipole antenna or some other antenna that gives you 7 dB gain in an omnidirectional pattern, or maybe it's a small Yagi pointed in the direction of the receive antenna. Okay, so that's your transmit power. You have 112 dB path loss. We calculated that. That's given to you for this frequency over this distance. And you have a receive antenna gain. This might be a reasonable estimate for a handheld antenna. Maybe closer to 0 dB would be good. And so you have the transmit power, you're going to add the antenna gain, you're going to subtract the path loss, and you're going to add the receive antenna gain to get the power out of the port. Okay, so PR is PT plus GT minus LP minus the path loss plus GR. Okay, so you get 30 dBm plus 7 dB minus 112 dB plus 2 dB. You get minus 73 dBm. Okay, so that's the value there. Okay, so if you were to calculate this power in watts, it would be 5.01 times 10 to the negative 11 watts. But I don't know any RF engineer, I'm going to make this general statement, any RF engineer that I've worked with or work with who thinks in watts for power that small, maybe as an intermediate calculation, but an experienced RF engineer receiving a narrowband communication signal looks at minus 73 dBm and would say, yeah, I could receive that. That would be pretty decent sound quality. We can work with that. If you tell them 5 times 10 to the negative 11th watts, they're not going to know. And the first thing they're going to do is calculate that value in dBm to see if it's reasonable. So just pointing out that we often work in dBm versus watts. We do use watts for some intermediate calculations, though. All right. Let's take a look back at the topic roadmap. We just talked about radio wave propagation and path loss, on how to estimate the amount of power that is seen by the receiver out of the antenna. Now let's talk about RF circuit performance. We're going to talk about noise and noise figure, signal to noise ratio, and these other metrics that are often used to characterize circuits and systems. Thermal noise is in every system, and in every RF system, and signal to noise ratio is a metric that we use to estimate the quality of a communications link. Okay, so SNR is the measure of the ability to determine the information represented by the signal. So if you have an analog system and you're listening to voice, right? If you know the SNR, you can estimate what the voice quality is going to be out of the demodulator. If it's a digital system and you're sending data, video, something like that, then based on the type of receiver, you can estimate based on SNR that makes it to the demodulator what the quality of the data is going to be, how many errors you will get, the bit error rate. There's a type of noise that is present in all circuits, and that is thermal noise. So practically you will always have thermal noise generated in your circuit and by your circuit. Thermal noise is actually caused by the movement, the random movement of electrons. So when electrons move in a resistor or a conductor, they're going to cause this noise. So if you take a real resistor that you put on the bench, you would actually model this resistor as an ideal resistor with no noise, a noiseless resistor, and a series noise voltage. Okay, so in the real world, when you have any kind of component that has resistance, even conductors have resistance, you're going to have this kind of behavior. You're going to have some kind of noise generated by that component. So that noise is going to look like this. It's going to be random, and it's going to have a zero mean of that passive resistor. And the characteristic of that voltage is going to be Gaussian. So if you took maybe regularly sample this signal, this voltage waveform over time, and then you plot those samples on a histogram, you would see a Gaussian curve, right? That bell curve that you're used to seeing. So in the time domain, that signal, that noise signal, looks Gaussian. I shouldn't say signal. I should just call it noise, because that's going to confuse everyone with signal. So that noise versus time is going to be Gaussian. In the frequency domain, that signal is going to be white. The noise is going to be white, and that means constant power spectrum. So the spectrum is going to look something like this. So when someone says white noise, what they mean is a constant, relatively power spectral density, right? That's watts per hertz, power divided by hertz, versus frequency. It's going to be flat. So when someone says white noise, at least over some reasonable spectrum, this is what they mean. That value of that noise versus frequency is going to be KB times T, where KB is Boltzmann's constant, and T is what we call temperature or noise temperature. So this is going to tell us for components in our receiver and our overall receiver what the noise is going to be like at any point in the circuits, right? So we're going to use this noise temperature value to quantify noise because that itself quantifies the power spectral density of noise delivered from a resistor to a matched load. So we calculate the noise power in watts using a specific bandwidth. So you notice that this is watts per hertz. Well, what if I just want watts? I want to know the noise I want to know the noise power. I don't want power spectral density. I want noise power. Well, every practical receiver has some bandwidth. It has some filter. So you're going to filter around some spectrum, and you're going to multiply that bandwidth times the power spectral density, right? If it's, let's say it's a rectangular bandwidth, and you'll get power. Okay, so that means noise is equal to KBT times the bandwidth, where B is the noise bandwidth in hertz. So if it's a perfectly rectangular filter, then the bandwidth is going to be that filter's bandwidth. And if you have some kind of shaped filter, it's going to be slightly different than the filter's 3 dB bandwidth. Okay, this is, if you go back to where I talked about filters, we were talking about what you can use them for. One thing I said is you can reject out of band signals. So one radio station doesn't interfere with another radio station at your receiver, right? If you're listening to FM radio. Well, also, and I also mentioned that the filters limit the noise into the receiver. So you want to make the filter narrow enough so that you reject noise, but wide enough so you don't distort the signal. So this is where that comes in. You want to make the filter as narrow as you can so you reject the noise. So this B is small as you can make it without distorting the signal. And that gives you a lower noise, right? And that gives you a higher signal to noise ratio, which is what you want. You want high signal to noise ratio. So SNR, signal to noise ratio, is simply the signal power divided by the noise power. If you express that ratio in dB, you get this. SNR in dB is 10 log base 10 signal power over noise power. If you have signal and noise in dBm, then it's just signal power in dBm minus noise power in dBm. Now, I want to give you an idea of what this looks like. Like, how do you visualize what a good SNR and what a bad SNR is? Now, as far as performance, different receiver techniques deal with signals differently, and some receivers can receive really low SNR signals and do just fine, give you the information back, use error correction coding, use integration and despreading, and we won't get into that. And some receivers aren't so good, like your FM radio in your car, right? You drive behind a truck or you move forward at a traffic light, you get into a fade, and all of a sudden your music gets all staticky. Okay, but I want to give you visually what it looks like if you were to apply noise to a sinusoid or have additive white Gaussian noise applied to a sinusoid, added to a sinusoid, what the SNR would look like, what the signal would look like. So if you take a clean sine wave and you add noise to it, Gaussian noise, and the SNR is 20 dB, this is what that signal would look like, right? It doesn't look too bad. You've probably seen waveforms like this on the oscilloscope in lab, right? You're looking at a really small waveform. Maybe it's, 20 millivolts or 30 millivolts or 100 millivolts, and you see some noise on it. It might look like this. Well, if the noise magnitude looked about this big compared to the sine wave, that was about a 20 dB SNR. A 10 dB SNR would look like this, right? This is looking a little worse. You can still kind of see it's a sine wave, but there's quite a bit of noise added onto that signal. A 0 dB SNR would look like this, right? So you can see the blue sine wave and there's the clean sine wave, and then I add the noise and you get the orange. So that's a pretty noisy signal. right? If that were audio, it would sound pretty bad. But that gives you an idea of different levels of SNR. Next, let's talk about common RF performance parameters. So there are some pretty common metrics we use to evaluate components and subsystems of transmitters, receivers, and RF systems in general. So our goal in the end is to efficiently and cost effectively communicate information with good enough quality. If we try to make the signal as perfect as we can, it's going to be really expensive, really big, take a lot of power. So that's why I say practical goal. We want to efficiently and cost effectively communicate information and get good enough quality, sufficient quality at the other end of the link. And so we want to maintain high enough SNR, not perfect, but high enough, and low enough distortion of the signal so that we get a good enough quality signal at the receiver. And we also want to use, usually, especially if we're battery powered, minimum amount of power from the supply, because this impacts the supply requirements, right? You don't want to transmit 1,000 watts if only 10 watts is needed. You don't want to use too much transmit power because your battery life will be short, right? And when you use RF amplifiers, they typically have an efficiency, depends on the type of amplifier, the type of waveform, but you could be looking at 15 to 40% efficiency. It varies depending upon the system, but that means there's a lot of power going into heat. So you could have thermal issues if you try to transmit more power than is actually needed, and that's going to affect your mechanical design. Okay, so there are some common performance parameters of systems and components that relate to achieving these goals. Let's take a look at an amplifier, right? Let's just take a connectorized amplifier. This is a mini circuits amplifier that I pulled out of the catalog. It's a low noise amplifier. It works between 400 megahertz and 3 gigahertz. It's 50 ohms input and output, and it has SMA connectors on it. And so this is the entry you will see in the data sheet or in the amplifier selection guide. These are the typical metrics you'll see. Frequency range. This is the band over which this component meets the specified performance. You can use these amplifiers sometimes outside of band, but you're not guaranteed to meet the other performance metrics. Here's power gain. That's P out over P in. Right? So when you're operating within the specs, this is the kind of gain you're going to see. This is typical gain for an RF amplifier. Right? The typical RF amplifiers maybe down to in the high single digits up to, for power amplifiers that have multiple stages, 40, 50 dB. You'll see noise figure. We'll talk about that, but that's a measure of how much noise this amplifier or any component adds to the signal. And this makes the signal to noise ratio worse. So you don't want that. You typically want a low noise figure. Low noise figure is better because that means you're adding less noise to the signal with this component. There's 1 dB compression point. This is the maximum output power above which the gain will fall more than 1 dB. So this is called gain compression. You'll have a lower gain because you're saturating that amplifier. You're clipping the signal if you try to output too high of a voltage, too high of a power. Okay, and then there's output third order intercept point. This is a measure of the linearity of the device. Linearity is good, non-linearity is bad because non-linearity causes signal distortion. It changes the shape of the waveform and it causes frequency products. It causes signals to happen at other frequencies outside of the band you're interested in, and it causes undesired spreading of the spectrum that you're generating or trying to transmit or receive. There's voltage standing wave ratio, VSWR. Some people just call this SWR. But VSWR or VSWR is a measure of how well the load resistance matches 50 ohms for maximum power transfer. So the input VSWR is really how well the input of this amplifier matches 50 ohms, and the output VSWR is how close the output impedance, that Thevenin resistance, how close that is to 50 ohms if it's a 50 ohm amplifier. And then you have voltage and current listed here. And so these are power supply requirements for usually when the amplifier isn't amplifying anything. It's just sitting there powered up with no signal in, no signal out. It's the quiescent power consumption that can change as it's operating. So you will see these for many RF components. You'll typically always see gain. If the component affects linearity, you'll see IP3. If the component adds noise, you'll see noise figure. So these are the performance metrics that are typical. Okay. These parameters vary over frequency. So when you see this for this amplifier, you'll also see plots given for systems and components that show, well, at 400 megahertz, you might have a different noise figure than up at 3 gigahertz. Let's start talking about noise figure, because we just talked about noise. We talked about additive white Gaussian noise. We talked about it. Every component is going to add some noise, and that's going to affect signal to noise ratio and affect the performance of the link. So noise figure is that figure of merit that quantifies the degradation of SNR, the lowering of SNR due to thermal noise. And this thermal noise is added by, well, every component you put into the circuit. So if you have a device and you have a signal to noise ratio in, so there's some signal coming in and with noise added to that signal, and then you have an SNR out, the SNR out is going to be worse than the SNR in other words, lower. Noise factor, right? Noise, not noise figure, but noise factor is that ratio. It's signal to noise ratio in divided by signal to noise ratio out. And actually when you have a standard amount of noise coming in, okay, that's what noise factor is. In noise figure, it's weird that they do this. We just accept that this is done. Noise figure is the dB value of noise factor. So take the dB value of noise factor and you get noise figure. So noise figure is in dB. Okay. SNR in is always larger. It's always better than SNR out. So noise factor is always greater than 1, and noise figure is always greater than 0 dB. Okay. So we talked about noise temperature. We use noise temperature to express the power of thermal noise within a given bandwidth. Right? We have AWGN, additive white Gaussian noise, and I introduced this noise power is KTB. Okay, so noise figure for a device is specified using this standard input noise temperature. So when you have this standard temperature T naught of 290 Kelvin, that's what we use when we're defining noise figure as SNR in over SNR out. Take the dB value. So we're going to talk about an additive noise model. And this additive noise model is this. You take a noiseless amp, or you pretend your amplifier only has gain, and it has a signal in and a signal out. And the signal out should be the gain times the signal in, right? If we're working in ratios, not dB. The noise in is KTB, and T in is this T naught value here, if you're representing this amplifier with this model. And then we have an additive noise, which is K times T sub A B, and T sub A is the amplifier's noise temperature. And then N out is going to be the gain times KB times the sum of those noise temperatures, right? We have the sum here. You're summing those powers, and it's equivalently you're summing those temperatures. So you can actually just sum the temperatures and figure out what the noise power is at the output after you multiply by gain. Okay. And so this amplifier's noise factor is SNR in divided by SNR out when the input noise is T naught, okay, which is 1 plus TA over T naught. Okay, so just to finish this up, noise figure for a device is equal to SNR in over SNR out when the input noise temperature is T naught, that 290 Kelvin value. So those are some details on how to model a device. This is how an amplifier would be modeled, or actually any device that has an input and an output, a gain and a additive noise. So what we're going to do next time is we're going to use this concept of noise figure and say, okay, I have noise figures for each individual component. How do I put this together into a cascaded system and then calculate the noise figure for the overall system? And that way I know, let's say that system's a receiver, then I can estimate the performance of the receiver and what the signal to noise ratio is for a given received signal. All right. So let's end this here. So don't forget, homework 8 is posted. Lab is all done. Congratulations on finishing that project. Be sure to turn in your case for your components and clean out your locker and leave the lock hanging there unlocked on the locker. Check out Canvas for the upcoming final few lectures and assignment date and due times. I will hold office hours in just a few seconds. So if you would like to chat, please stick around. If not, I'll see you next time. Have a great night.